All right, so nice to meet you all. This is quantum computing class, and I'm gonna start by calling out your names. So today we're gonna have a brief introduction to our syllabus, and then small material to understand the quantum computing throughout the semester. So let me call out your name first. 고민재, 고우상, 권병준, 김도훈, 김동현, 김민준, 김병규, yes, 김여진. I forgot the pen. Do you have pen? I'll get back after class. Okay. 김현호, 김형근, 문수민, 백원중, 송현주, 염장훈, 유연식, 윤경훈, 이현준, 이호준, 임정민, 정혜주, 최서하, 최준호. Okay. So you can check out the contents of the syllabus from the portal. So nothing much is different. Nothing much is changed. I mean, actually, nothing is changed. But I just want to emphasize that our grading scheme. So it's not changed from the syllabus. Just re-emphasize again. So we have midterm, which count of 30%, and final 30%, and we're gonna have a quiz. That's gonna be 30%, and I'm not gonna announce before I get a quiz. I'm gonna have a random quiz at any random day. So if you miss the quiz, no chance unless you notify me your absence beforehand. And the last one is attendance, 10%. So far, the previous semesters, I had a project, but I decided not to have a project in this semester. But it doesn't mean that you don't need a project. So after you finish this course, what I'm expecting you to have is some idea what you going to have to study about something related to the quantum computing. So if you have something in mind throughout the semester about the quantum computing that makes you do some project, let me know if I can help as far as I can. And yeah, that's basically all I have to say. But if you have any questions about this course or about the syllabus, let me know before we start. By the way, so grading scheme. So this is the grading proportion. Grading scheme is, so I always use this scheme. So so there are four, A, B, C, D, right? So F is when you miss one of midterm or final, or you have missed class more than 1/3 of the class, then you get failed. So unless you take all the midterms and finals and attendance, you're not gonna get F. So basically, my grading scheme for every class is the following. So you get, A0, A minus. So you get A plus when when scaled at 100. If you get more than or equal to 90, then you get A plus. If you get more than 80 or above, then you get A0 and 75 for A minus. So B plus, the scale goes similar. So we get B plus, which is over 65 and 55 and 50. So you can see it's very, so in my estimate, it's very hard to get C or D if you just do your work. But um, if you're worried, yeah, if you get these scores above, then you get that grade. So I never see someone who got D unless they drop in the middle of the semester. So any other class? Any other questions? All right. Um, so I'm recording all the lectures. So if you want to rewatch the lecture, you can go to the. I'm gonna upload the link on the LMS site. You can go to that website to see the video clips. All right, so let's talk about the quantum computing. So we need to know what we're learning here. So, so what is quantum computing? So it's not a quantum mechanics. It's not quantum information. It's certainly not quantum optics. It's not quantum computer. We're talking about quantum computing. So what is it? It's a study of quantum algorithm and quantum error correction. Those two things, quantum algorithm and quantum error corrections, are the two main things in the quantum computing. So if you look at any quantum computing book, most of them are written by physicists. So they often talk about, let's say, Schrödinger equation or wave function, sometimes density matrix. But I'm not a physicist, so let me be clear that I cannot talk about anything about the quantum mechanics, any deep knowledge about quantum mechanics, or something related to that some physicist developed. But I can surely talk about these two things. And as I study myself about the quantum computing, these two are the main topic. So what is quantum? So basically, these are something that we really need to know if you want to implement the quantum computing into real life. So let's say you want to compute something, you need a computer, the hardware, right? So that means you need a quantum computer to do some quantum computing. So where this quantum algorithm used? It's the circuit, quantum algorithm is circuit that you can implement into real quantum computer to do some computation, actual computation. And what's the quantum error correction? It's the device, it's the scheme that you need to implement into the quantum computer when you build a quantum computer in the very beginning so that your quantum computer works properly. Because quantum computer nowadays, I don't know whether it's going to be developed in the next future, but so far, quantum computer has so much error rate. So it's not that quantum computer is wrong, it's just that quantum materials are very unstable, so they need some scheme to correct the error. And normal computer, the classical computer, also have errors. So they have also error correction scheme. but that error is not a sphere unless you need a real precision. But in quantum computer case, errors are everywhere, so you definitely need error correction. So and then there's no single type of error correction method. You need to study it, you need to develop one. And so far, the most prominent error correction code is the surface code, but people never have an actual quantum computer implemented with the surface code. So there are many problems why they didn't implement the quantum error correction. The one is that the material that they have in the quantum computer is not fully studied yet. So we need physicists who study quantum material to develop more stable and reliable material. And also, we need also study some error correction to improve the efficiency of the error correction. So these two are things that we're going to talk about throughout the semester, not in full detail because the study of quantum computing is still developing, and I certainly cannot cover entire the theory that is available. So if you find something very interesting, you can study on your own, and if you want to bring up in the class, you can always do that. Let me know. All right, so okay, so why? So I'm going to focus on, so as throughout the semester, whenever I introduce a topic, I'm going to focus on three things: what, why, and how. So I hope that you can get this kind of way of thinking when you study anything. So let's say, okay, let's ask, why do we study quantum computing? Why? I mean, this must be, you guys have to have answer because you already took this course. Why do you think the quantum computing is important? Why do you take this course?
I think that some quantum computers are developed in physical form.
Yes.
And there are many research for quantum algorithms.
Yes. So you want to know them. Yeah. So why do you think it's important to know those quantum algorithms?
The quantum algorithm can solve something difficult for classical computers.
Right, yes. So quantum computers are known to be a device that can solve a difficult problem, which is almost impossible to solve with classical computers. So to solve a difficult problems for, so okay, so let me write. Classical computer. So we're going to separate two types of computer whenever we need to talk about the computer throughout the semester. One is the quantum computer, the other is the classical computer. So what's the difference between quantum computer and classical computer? Classical computer uses bits. Bit 0 and 1 is the unit of data for every classical computer nowadays. But quantum computer doesn't use bit. Bit is not anymore the information. It uses qubit. We're going to talk about qubit this class today. So anyway, for computer that uses bits, some problems like a graph coloring problem, known as NP-hard problem, are unable to solve. A mathematician already proved that you need the same amount of time to find an answer and check whether your answer is optimal. So basically, there's no genuine way of solving the question unless you find out all the possibility of the solution and then check everything, whether that's true or whether that's solution or not. So, but quantum computer could solve, and I say it does not solve the problem in a way we want, but it actually excels the speed of solution, speed of solving the problem for classical computer. So there's something, uh, some complicated story going on. So if I say, okay, quantum computer can solve any problem, then that's definitely false. So it cannot solve any problems. For some problems, they haven't found out any quantum algorithm solving that questions. And for some problems, you need some probabilistic chance that this quantum computer can solve that question. So anyway, so that's basically why. So anyone wants to add more questions, more answers to why we need quantum computer? Anyone wants to share why do you take this course? What's your reason taking this course?
Reason for the personal reason was actually to I was interested in quantum computing itself. It was and the algorithm it uses would look very intriguing to study.
Yeah. So what part of quantum algorithm intrigued you?
I first saw the Grover algorithm,
Grover's, okay.
which can find some element within time less than n.
Yes.
And those kind of algorithms actually look very fun for
Yes.
me.
Mm-hmm.
I think there are a lot more algorithms to research in quantum computers rather than in classical computer.
Mm-hmm.
Or
Yep.
yes, so
Yeah.
that's the reason.
Mm-hmm. Yeah, I mean that's the important part because basically that's why I began to study quantum computing. Basically, it's fun. Why is it fun? Because nothing much is already known. Nothing much, almost nothing is known yet. When people are studying a lot for quantum error correction, or if you get to the quantum algorithm part, unless I mean, apart from the Shor's algorithm and Grover's algorithm, which are the most two famous algorithms, so far, nothing is known, nothing effective algorithm is known. People are talking about how to implement quantum algorithm into AI system. Basically, the ideas are same, but they didn't find out a genuinely nice way to introduce AI in quantum computer. But do you know how old is Shor's algorithm and Grover's algorithm? Like it's more almost 40 years ago they developed those algorithms. For 40 years they have all the theories, even though they didn't have a quantum computer or any idea how to make a quantum computer. They developed the quantum algorithm, which is most effective so far now. And Shor's algorithm, because of Shor algorithm, they never implemented Shor algorithm in any computer to solve any crypto. But because of that, people are thinking about quantum safe crypto system, and they already found that this some crypto system that is uh, safe with a quantum computer. So, but as I said, nothing is known other than nothing fun is known. Nothing interesting is known other than Shor's algorithm and Grover's algorithm. So it's very fun to study it, to discover what is unknown. All right, so how do we study quantum computing? So I would say it's very interdisciplinary subject. It's sad to say that almost all quantum computer scientists are physicists, but um, it's a mix of physics, mathematics, and computer science. Okay, so briefly, let's see why. Well, okay, we need quantum computer, of course. We need the material, we need hardware to actually implement quantum computing algorithm or error correction. So we cannot talk without thinking about the realization of the quantum computer. So we need some physics. We cannot just randomly say anything. And also we need to rely on some rules, the theory, a principle that physicists already found in quantum mechanics. So we need physics. But as I said, I'm not a physicist, and I don't have any deep knowledge about quantum mechanics. So I'm not going to talk why that is, how they developed. I just lay out the fact. I'm going to use that as an axiom. So that we need to just accept. And the second part is the mathematics. We need mathematics. We need more mathematics than classical computer or classical algorithm, because all the quantum computing business is about calculating things. Not just calculating numerically, it's calculating in rigorous way and prove rigorous way why that it happens, why that is true. So there are some saying that if you, let's say, in quantum mechanics, there is a fun saying that shut up and start computing, something like that. If you're not sure about why the quantum mechanics works that way, then there's a famous saying, shut up and just start computing. So if you compute things, then it makes sense. So it warns us not to rely on our intuition when dealing with the quantum mechanics. Same for our quantum computing business. You will see that something is very weird in some cases. So for example, if you go to the entanglements business, it's certainly out of our intuitive thinking. So, but when you take the computation, when you just write down the equations and formulas, it all makes sense. So we need mathematics. And of course, the last one is the computer science. We need computer science because most of the questions we are dealing with are coming from the computer science. And why is that? So we're going to talk about the qubit that I mentioned before. And the qubit itself is not something we can find out what that is. So we need to measure the qubit to find out whether it's turned out to be 0 or 1. So all the information after going through all the quantum circuits and quantum algorithm, all you get is information of 0 and 1. So basically, you turn back every quantum information into information of bits, which classical computer can deal with. So in that case, we also need quantum computer. And also in quantum algorithm, you definitely need aid of the quantum classical computer. So we need quantum computer science. So, but I think as we progress, well, I'm not saying one subject is more important than the others, but we're gonna rely heavily on mathematics part and computer science part, not so much on the physicist part, unless for the first part in our semester. Okay, so that's what, why, and how. Any questions about? So this is the brief overview of the quantum computing that we're going to learn about. Any questions about these? Yes.
Could you introduce the application of quantum computing for another
In another
study?
another study?
Like,
Yeah, I don't know anything, any application of quantum computing in chemistry. Other study, well, I heard that there is an application to AI, but not, I haven't found any effective. If I found any effective studies on AI, but you probably have heard it because I never studied deeply what's going on. Well, what I can introduce is the old theory of Shor's algorithm. So that leads to solving RSA inscription. So just a brief introduction. I'm not going to go into deeply, but I can't right now, and also I don't have enough knowledge to introduce fully what's going on unless I prepare a lot. So so Shor's algorithm is basically, it's not coming from nothing. It's based on lots of physicists who developed artificial or imaginary problem which the quantum computer can solve effectively than the classical computer. And Shor come up with a very nice idea, and then people later found out that, okay, this actually can be a solution to RSA encryption. So now they are in trouble because they know that if the quantum computer is out there, then every encryption is endangered, and they need to find quantum proof crypto. And then this is basically a mix of mathematics and computer science. And I just list all the things that I know so far. So they also have, so there are, we're gonna talk about this in one class in 1 week of our semester, but there is actually two types of quantum computer. One is universal quantum computer that we're going to talk about, and the other is actually quantum annealing. So quantum annealing is actually different quantum computer, but relies on quantum mechanics. And quantum annealer is actually out there. You can put your hands in and you can actually solve some simple questions. And in the quantum annealer question, you can actually solve some problems um, with some algorithm optimizations methods. So you can solve an optimization problem. So if you want to find any application of quantum computer, basically you want to find a solution to a problem, and most of the problem is finding optimal solution. So you want to go for a quantum annealer if you really want to solve right now your question. So, and the question is how to formulate your question that suits to this particular type of quantum computing. So we're going to talk about this briefly in our semester too. And yeah, I heard something about AI, but as far as I know, every time I saw or read or listen about the application of quantum computer in the AI business, it doesn't really give a genuine idea how to break through the difficulties of AI currently now. Because I think, first of all, they don't need a quantum computing for AI, really, because they already achieve a lot with the classical computer to make a powerful AI that we can experience right now. And also, so basically, I think my understanding is the people who trying to apply quantum computing in AI is it's kind of theoretic. So what does AI do? So what I mean by theoretic is that basically you want to find an optimal solution, right? So that's the AI. What is AI do? So it's basically optimization. So if you want to find the optimal solution, if you know all the possible solution, you can just plug in that numbers and then find out which one is optimal. But you can't because you don't have much time. So, but in the quantum computer, what happens is you can make every possible solution at once. You can make every possible solution exist at once in one solution and then check all the solution at once. So basically, people are theoretically thinking that quantum computer can make AI faster and effective because it can lay out all the solution in a one quantum state, and then you can just put that into a circuit, a big circuit, and then find out the solution, optimal solution at once. That's basically correct idea, but practically, so far right now, the AI works well, and people don't have need of classical computer to use a quantum computer implemented in AI. And all the studies is somehow not, not too different from what have we already done in the classical situation. So that's all I can say about the application. So, but if you find out any applications, then you can certainly study on your own and also introduce us about your study. Yeah, so thank you for bringing up the questions. Any other questions before we move on? Yes.
I've heard that the universal quantum computing is not completed.
Yes.
What kind of the aspect is not completed? I want to know that the errors or the unsolved problems
Mm,
about it.
okay. So in the hardware business, the most difficult problem is finding a material, quantum material that is stable under reasonable circumstances. So far, Google or IBM has a real quantum computer which has a very few qubits in it, and they have to contain it in a very low temperature, like almost up like absolute zero. So in order to make their quantum state stable for a microsecond, so they have to finish it until all the quantum information breakdowns. Um, so it says its technical term is decoherence. Um, so this is already a few years ago that, but they try. Some people, I mean, some physicists in some labs are trying to find a new material called diamond defect. So it's a MP4. I forgot the name. So it's a kind of a defect in the diamond, and it has a quantum characteristics that then they can contain quantum information in a normal temperature, like a 20 Celsius degree, and then it lasts for milliseconds. So way better than um, the quantum computer we have it right now. But the problem is the error rate. Error rate is so low that, I mean, if you can't find the reliable information, even though even though you have a lasting information, lasting quantum information in a quantum material, what's good for? So yeah, so far, and because it's working, the quantum computer that is working is a semiconductor with a very high, very low temperature, and also sealed it with a very thick layer to prevent all outside turbulence, like a magnetic force and so on. So therefore, they couldn't make it large. They cannot scale it because if you make it bigger, you need exponentially large amount of volumes and also the energy to contain all the environment safe. So that's the difficulty, main difficulty, having a quantum material stable. And also, um, yeah, so the question is scaling. They need lots of qubits in order to solve big questions, big problems. So for example, RSA, um, like there are 256-bit RSA, 515, 512, and they don't even use this anymore. They probably use 4000 RSA, 4048 or something like that. So if you want to solve this question, I mean, if you really want to use quantum computing to break some code, like the military secret or something that you really want to break um, secretly, then you need large computer. Large means that it has a large qubits. How can you make that? I mean, you cannot make. I mean, there are certain limit to the size, the small size of the qubits. So if you have a larger and larger qubits, then your computer gets larger and large. People never didn't find out how to scale it up. So I think my perspective, it's like ENIAC. So in the classical computer, a long time ago, ENIAC was as big as this room. Now it's as small as our tiny finger. So for some right now, if you see the picture of quantum computer, like it's very monstrous, scary thing hanging on the ceiling or standing on the big room. But maybe physicists find out some magical materials, or some theory that can make into smaller part. So we don't know, but as I said, what we are doing in the quantum computer is when such quantum computer is available, when a large-scale quantum computer is available, then we can implement whatever we want, whatever algorithm we want into that quantum computer to solve the problem. So in the semester, we're gonna put our hands in our IBM Q experience. So that's, I'm not sure whether it's still free, but it was free a few years ago. I haven't tried since then. You can actually make a circuit in uh, that circuit on your own, and then put that into a real quantum computer. So IBM let us, everyone, to freely use their um, low quality quantum computers for us, and it takes about 30 minutes to get the result, but actually they get the result, they give the result. So when you see that, there is always an error, not that much because it has a small qubit, but you will find out that you cannot do anything other than just see what is supposed to be, just to checking what it's supposed to be, but you cannot do anything with that small scale quantum computer to solve any practical problem. So yeah, the scaling is the most difficult problem here. Does that kind of answers your questions? Do you have any other concerns?
So according to so the main problem and so the main goal of the universal quantum computing is focused on engineering.
Yes, basically, yes.
Now
Good summary.
the main problem is the engineering problems and how we can continue and we can maintain the state-so quantums,
Mhm.
the time problems or
Yes.
maintaining problems,
Yes.
the real problem. It can be more mainly.
Yeah. Yeah. So I think I don't know much about the classical computer, but they're still developing how to make classical computers small. But because if you make it small, you can make it powerful, right? With the same amount, you can have more transistor in it. So basically, the same thing going on in quantum computers. They have one, but they want to make it small or reliable, whatever, or make it bigger. But they don't have, I mean, they need a lot of time. It needs a lot of time. So because of that, some people doubt that quantum computer will ever accomplished. Because if you don't have a quantum computer, everything is just nonsense. We don't have any application. So some people, really few people, doubt that this quantum computer will uh, be actually be out there to solve our problem. Um, but for my case, I just I just I just want to have fun because people have thought about it. Many people have thought about it. I believe they're uh, like big scholar. They are big scholars, and I believe they have good intuition why that is must be true. And I would just want to put some efforts on it to find any small detailed progress on this subject, um, because because I think nothing much have done in the mathematical perspective. Most have done in the physicist perspective and computer science, but I just want to do something in the mathematical part. Yeah. All right. So, any other questions? Okay. So let's talk about the qubits. So when you, so I'm going to define everything, which you might not find in any book because most of the books try to describe something, describe the term and object, but I just want to define it. So, but if you see the definition, it's kind of a bit weird because when you define something, I'm defining it on an abstract level, but qubit is an actual reality. You have a qubit in your hand in your quantum computer, but it feels like it's different from the definition, but I'll just define it. So what is qubit? Is the unit quantum of unit of quantum information. Okay. All right. So I know that's a unit. What is it then? So let me define more specifically. So a 1 qubit state. So qubit is like some general term. It's about a vague idea. It's an abstract term. So I just need to introduce another terminology that's specifically used in the quantum algorithm. A 1 qubit state is a one-dimensional complex vector. Okay. So here are lots of terminology you might not familiar, or maybe you forgot. So I just want to introduce everything in detail, use full generality. So here, so what is meaning of one-dimensional? What is the complex? What is the vector? Okay, so let's talk about complex number first. So a complex number is a number system that satisfies the following property. So first of all, it has so first of all, it has a representation with the linear combination of real part and imaginary part. So any complex number say Z is a linear combination. So I'm going to introduce some mathematical terminology, but I'm going to add some comments on it. So whenever you see the linear combination throughout the semester, just think about its addition. Okay, so it's added together. So simply so it's added of. So let me write the capital letter whenever I introduce the new terminology here. The real part X and the imaginary part Y in the following way. So whenever you write complex number, you write this way. So you have X, X added to Y, but Y you need to multiply I. So I is just a symbol. Okay? So I introduce what I is. I is just a number, complex number. So if you have X equals to 0 and Y equals to 1, that becomes just I, right? That's not all the properties, just the one property. And then second property is, if you have two complex number, let's say Z1, which is X1 plus I, Y1, and Z2, which is X2 plus I, Y2, then you can add them together to get another complex number. the following way. So we write Z1 plus Z2 to indicate that new complex number. And that complex number has real part, which is the addition of two real parts in two different complex number, and imaginary part, also addition of two imaginary parts in two different complex numbers. So that's your new complex number obtained by addition. And so already some of you know, or some of you ring a bell, you have a multiplication between two complex numbers. For two complex number, Z1 and Z2, let's say we have the same x and y's here. The multiplication Z1, Z2 is given by Z1 times Z2 is x1, x2 minus y1, y2, and x1, y2 plus x2, y1. Well, just the definition, but you can also remember this rule by simply distributing the x and y's. For example, if you have x1 plus y1 times x2 plus I y2, then just take it as a symbolically, you have x1 plus I y1, so you just distribute it along. We have x1, x2 plus I y2, and then you also distribute this I y1 here, I y1, x2, I y2, okay? And then distribute it again for each parenthesis here and here. So you get x1, x2, and well, let's not change the order here. So x1 I y2 plus I y1 x2, and then I y1 I y2. So I'm not using the definition. I'm just showing you how the definition could be memorized. So whenever you take the multiplication between two complex numbers, the real part and imaginary part, including the I, can be switched the order. You can commute the order of each symbols. Of course, you can commute the multiplication between two real numbers because it doesn't change. And you can also change the order of multiplication between the real number and the symbol I. So you can take it as plus I times x1, y2, and here you already have I outside. But here you also change the I and y1, you get I squared. And then let's just go back to the definition here. What happens when you have z1 and z2 equals to I, where x1 and x2 are 0 and y1, y2 are 1? You get minus 1 here, and everything is 0 outside here. So you get I times I is minus 1. So the I squared is minus 1. So you combine the real part and imaginary part again. So this is the real number. This is the minus y1, y2, which is also a real number. So you can combine them together. And then just take the, now you factor out with I. You get x1, y2, y1, x2. Okay, so if you want to put the parenthesis, now you get the result. So I'm just saying that this is how you could just memorize, or you make the computation simple. Although this is the definition, you don't have to memorize. You have to try to memorize all this complicated definition. Just do the computation as if they are all the real number, but don't forget that I squared is -1. So this is complex number. This is basically complex number, but we need to know something about the complex number. Okay, so let me introduce some properties of complex numbers. So far, we're not going to talk deep about the quantum algorithm. Just I want to know what is the qubit here. So we need to understand the complex number because that's the core. That's the core object that you need to understand what's the qubit. So first of all, the real number 0, just the real number. So you can consider this as 0 plus I times 0. So it's also considered as a complex number, is the identity to the addition of complex number. So what do you mean by identity? It means that if you add any number to 0, you get the same thing. So that means, i.e., for any complex number z, 0 plus z, also z plus 0 equals to z. So nothing changed. So 0 has identity. And let's think about the real number 1. So the real number 1, so it's also a complex number because you can set the real part as 1 and imaginary part as 0. So is the identity to the multiplication. Which means that for i.e. for any complex number z, 1 times z or z times 1 is always equals to z. Well, that's obvious if you just look at the definition of multiplication, and also if you think about the rule of distributing the real numbers and real part and imaginary part, that's obvious. And we can talk about the inverse in real addition and inverse in multiplication, but let's skip to this part. So let's say the norm, or sometimes it's called size, of a complex number set given by x plus yi is the real number is let's say is denoted by the absolute value of z, or same absolute value as the real number. Okay, it's the same symbol, and is defined as follows. So we have square root x squared plus y squared. So it's a real number because x and y are real number, and these two numbers added together is always positive real number. It could be 0. When you take the square root, it always is a real number. And we have another terminology. Whenever you have a complex number, you can have a conjugate of complex number. The conjugate of z denoted by z bar is defined as x minus iy, where z is defined as x plus yi. Your conjugate only changes the sign of imaginary part. The imaginary part of the original complex number is y, where its conjugate has minus y, now changing the real part. And when you have a conjugate, you can find out the inverse of the complex number and satisfies the following. If z is not 0, then 1 over z is z bar over square of the size or norm of z. So you can find a norm of z easily by taking a real number like this. And also what goes on the top in the numerator is the z bar. So your inverse, multiplicative inverse of any complex number whenever it's not 0 is computed easily by this formula. Basically, it's kind of obvious because let's think about the square root. Square of the size of z. It's the square of the square root. You get x squared plus y squared. So it's kind of a proof of the last fourth proposition here. And you can get this by taking a multiplication of two complex numbers, x plus iy and x minus iy. And if you plug in that to the definition of multiplication, you see that it's actually x squared plus y squared. So it's z and z bar. So if you think about, if you replace the square of the size of z, what you get is z bar. So you get the canceling out of z bar, and top and bottom, basically you get 1 over z again. So this is the simple identity here. So sometimes it's useful to find out the real part and imaginary part of the complex number, the inverse of the complex number. And then this is the most important part. So another proposition of a complex number is that you have Euler formula. For any complex number, we have the identity, which is e to the iz equals to cosine z plus I sine z. So this is going to be used a lot throughout semester. I mean, maybe if you first part and when we're dealing with the Shor's algorithm. And what does this say? It's very weird. This is not the same Euler formula you've probably seen in the engineering mathematics 1, because in that case, we had a real number instead of a complex number. Here, that is a complex number. What do you mean by complex number inside cosine and sine, and also in the exponential? So if that is theta, the real number, just the real number, mean that the imaginary part is 0, then this formula becomes e to the I theta cosine theta plus I sine theta. So that's familiar, maybe. Let's see. If it's not familiar, that's okay. I'm going to show you why this is true. But there are many ways to interpret this formula. So before we talk about this formula, let's talk about this formula, the special case. So one way is to use the polar coordinate. So theta is the angle between a point in the two-dimensional plane with the positive x-axis. So these two-dimensional plane can be considered as a set of complex numbers. Because if you take the horizontal axis representing the real part and the vertical axis representing the imaginary part, you can get a point identified as a complex number, x plus yi. So x is the horizontal axis or coordinate, and y, the imaginary part, is the vertical or vertical coordinate. And zeta is the angle between this line connecting the origin, 0 in this case, and the complex number, and the positive x-axis here. So what does that mean? So if you have cosine and sine zeta as an x and y coordinate of a point, that means your complex number, your point, is lying on the boundary of a unit disk, the circle of radius 1. So the e to the I theta is the complex number at angle theta on the unit circle. So that's one interpretation, and that's not certainly a proof. Well, let's prove it. So how do you define the exponential of something? There are many ways. The most easiest and most practical way of defining the exponential function is you use the series, infinite series. So 1 plus x squared, 2 factorial, x cubed, 3 factorial, and so on. Right? And how about cosine and sine? Okay, so of course the definition. So I'm assuming that x is a real number for now. Of course, the definition of cosine and sine is x coordinate and y coordinate a point on the unit circle. But when you really want to compute the value of cosine and sine, you need a series. So you can also define cosine and sine as a series. So what's the series of cosine x? When you expand it at 0 in the Taylor series form, you get 1 minus x squared, yes, x fours, forgot, 2 factorial, 4 factorial, minus. How about sine? You have an odd degree, x minus x cubed, 3 factorial, x fifths, 5 factorial, and so on. So let's now plug in I theta instead of x. So what happens when I plug in I theta? We have e to the I theta, 1 plus ix. Now we have ix in x squared, I theta in x squared. So I is squared, you get minus x squared, 2 factorial. And here we get I cube, so which is minus I, and x cubed over 3 factorial. And when it gets fourth, then I fourth is 1, so you go back to the plus. Okay, so let's take a real part and imaginary part together. So if you take the real part together, you get 1 minus x squared over 2 factorial. And the next one comes with the x fourth, so it's plus and minus again. So that's the real part. And the imaginary part, you have to factor out I. So I times x minus x cubed, 3 factorial, x fifth, 5 factorial, and so on. You see that it's a cosine. This is sine. Okay. So how does this work? So now I'm thinking about this. So let's talk about when x plus yi, when z is x plus yi. Let me plug in here. So then I can distribute I throughout this parenthesis. We get EIX minus y, right? Because I squared. So now it's also it's also the proposition of the exponential function if you define this way as a series that whenever you have two things added together, no matter what this is, no matter what these are, it can be either real numbers or complex number, doesn't matter. You can always split into two. So it's actually coming from the simple distribution rule when you use the series form. So we're gonna distribute it this way. Okay. And then what's this? It's cosine x plus I sine x times e to the minus y. And then what we have, so we have cosine x times e to the minus y plus I sine x e to the minus y. And let's try to compute this. Cosine x, what is it? 1 minus x squared over 2 factorial x fourths, 4 factorial, and so on. And what is e to the minus y? It's 1 minus y plus y squared 2 factorial minus y cubed 3 factorial and so on. So we can do the similar thing for the second term. We have I something times same thing here. Now, what's the end goal here? We want to show that it's same as cosine z plus I sine z. How do you get that? Well, it's actually complicated, so I'm not going to finish all the computation. We don't have much time. So I'll show you the way how it should be. So this is as far as I got. I can go further by taking a distribution among these two parentheses. But let's start from the right-hand side of that star equation. So what is cosine z here? Cosine z plus sine z. It also starts with the definition of cosine and sine, exactly the same form we defined earlier. So cosine z is 1 minus z squared over 2 factorial, z fourth, and 4 factorial, and so on. And then plus I sine z is z minus z cube, cube factorial, cube fifths, 5 factorial, and so on. So if you don't want this, you can just simply take z as x plus iy squared, z 2 factorial, and x plus iy fourth, 4 factorial, and so on. And then do the same thing for on the right hand side, and you can see that there are actually the same formula if you expand it to the lowest level. So that's one way you can prove it. Another way of proving it, well, actually, I have to admit that it's not the easiest. That's not the easiest way to prove this statement. We already proved it, actually. We already proved it when we have. Well, actually, it's not. Yeah, we already proved it when we proved it for the real number. So just consider x not a real number, just a complex number. Every arithmetic rule is true for the complex case. So instead of theta, well, yeah, I forgot. So it should be x, right? So, sorry, I should change it all x into theta, but it's going to be too much. So if I replace x with a z, everything is okay. So everything not wrong. You see, so just z times I is just z times I here. Everything else the same. So you got the cosine z, and this you got the sine z. But if you're not convinced, because these are complex number, these two are complex number, if you're not convinced, then you can break it down into the lowest level, like real number plus the real part plus imaginary part. And you can see that actually works by expanding everything here. Right? All right. So that's going to be used later. And there's so many things we can talk about, but let me just make a brief remark before we finish. So I'm going to talk a little bit next time we haven't covered. So here's the note. So how do we define the one qubit state? One qubit state is a complex vector, one-dimensional complex vector. But our question is, how do we represent, how do we write one qubit state? A one qubit state is denoted by ket. So linear combination of kets. What is kets? So this is ket notation. Yes, it's a vector, yes. But they call it ket. So it's not mathematician who named it, it's physicists. I don't know where it came from, but physicists wants to put some meanings on their symbols, but probably so this one has a meaning, but I don't know why. But it's a convention, so we have to follow that convention because most of the manuscripts are written in that convention. So these alpha and beta are complex number. And what about 0 and 1? So this is called 0 ket. And this is called 1 ket. We often call these 0 ket and 1 ket as a basis state. So every quantum state, every one qubit state is a linear combination, meaning that we have complex number multiplied to the basis state added together. And we take this whole state into a one symbol again, with usually a ket notation. And you can put anything here. I put the psi here, so it's just the quantum state. It's a traditional, conventional way of describing, noting the quantum state, one qubit quantum state here. So if you want to real name it, then it's psi ket, something like this. Okay? So why is this vector? Why is this matches with our definition? We're going to talk about this next time. First, we need to talk about what is vector. Because we define the one qubit state as a vector, we need to show how does vector property, vector definition satisfies in this notation. And also we're going to introduce another representation of quantum state and also a lot more about other types of vectors in the quantum state called bra. So people usually say bracket, right? The bracket. So it's a bracket here. So bracket. So I think that's where the name come from, but I'm not sure. But if you take this part is bra, this part is ket. So yeah, so far just remember how we define the quantum state and the ket notation. We'll continue the next time. If you have any question, let me know after class. Otherwise, we'll see you on Wednesday.